So that's our recording. So today we're doing the applications of your calc into kinematics. What's kinematics? Right, kinetic energy, moving, right, motion. So that's what this fancy word means, kinematics. All right, and
you can plug the USB into the computer.
I've plugged it in. So this is why I usually test all of these beforehand to make sure it's all working. So let's get started now. Sorry about that, we're now working. All right, so kinematics is just the fancy word for saying we're talking about things moving. We're looking at rates of change, and we're looking at optimism. So that's the main areas we're looking at today. All right, so your opening problem. Michael rides up a hill and down the other side to his friend's house. The dots on the graph show Michael's position at various times of t. So what we're noting here, we're just doing it as a straight line. We're not imagining him turning corners or anything. So we're just thinking in a linear manner. So he heads off at time 0. At time 5, he's travelled this distance. At time 10, he's now here. Time 15, he's now there. At time 17, he's moved on a lot further. Time 19, he's now at his friend's house. What's the first thing you notice about that timeline?
The spaces, they aren't the same?
Spaces aren't the same. Are the time gaps the same?
No.
No. So that's, time gaps are different. So in 5 minutes, he's gone this distance. Right, so there's your first 5 minutes. In the next 5, he did this much.
Does he ride up a really steep hill?
Right, he could be going up a really steep hill. All right, if that's too noisy, let's just shut the windows, but we need air. All right, so he's obviously going, let's talk like in kinematics, we're talking distances, we're talking speeds, velocities, acceleration. They're all the terms we're using that you need to understand. So what would you say is happening if he's gone only a short distance?
Accelerated.
He's
Accelerated?
decelerated,
Yeah.
like he's going slower. Right? Because he hasn't travelled as far in that 5 minutes. Velocity's decreased. Yep. Can I just I'm doing a quick aligning to see. In that between 5 and 10 minutes, did you notice that it was now slightly longer? What do you say about his speed?
It increased slightly.
Increased slightly. So he's got a little bit faster, but still much slower compared to in the first 5 minutes. What can you say now about his last 5 minutes?
He's gone onto the street, it's the final sort of stretch.
Oh, he's going downhill.
Or he's going downhill, he's powering it. So really fast because he's travelled a big distance in that 4 minutes. All right? So we can look at and describe his movement in a straight line like that.
Should we write this down?
No, I think at the moment I just want your understanding and thinking. All right? So the distance that Michael's travelled at various times is given by this function. So what we've done now is be able to describe how he's moving in an equation. So how do you get that equation? So if we graph this, so this graph here is now, it's not saying that's what the hill looks like or anything. This is now saying in the first 5 minutes, he's travelled this distance. So this is your distance from home up this vertical axis. So that's your, what we call S for displacement. All right? So important thing here, that S, because they don't. S is for displacement. It is not the speed. All right? I had a student once who got through about 2 months and then suddenly she realised, oh, S is not speed. But that's okay, because like you're not, it's not okay, but it's like you're not used to it. It'd be nice for D for displacement, but they don't. They use S for displacement.
Wait, D for distance as well?
And we're going to go into that. All right. So this is saying now at 10 minutes, that far from home. At 15 minutes, this far from home. At 19 minutes, at his friend's house. Okay. So I'm doing a quick overview, then we're going to go through all this in more detail. So here's our curve. We've modelled it using some clever maths or regression to come out with our equation. We've just been doing calculus. What have we been looking at? Derivatives, which are gradients of
A curve. A point on
a
a curve.
tangent to a curve. You cannot take the gradient of a curve because it's curved. You can only take the gradient of a line, of a tangent. So what we could be doing then in all these cases is saying, what's the gradient of that tangent? What's the gradient of that tangent? What's the gradient of this tangent? So we could be talking about gradients of a tangent. What are the gradients or the tangents telling us?
The rate.
The rate of change.
It's the velocity. Yeah, it's how fast he's going at that moment. All right? So the tangent is, so if you think back, rise over run, it's this axis, the change of distance over time. All right? So it's telling us how fast.
There we go.
Yes, but I've got all these in the coming board. I'm just giving you a big overview to get you to picture what we're talking about. Explain why this function should be an increasing function.
Because he's constantly gaining distance.
You can't go negative
Yeah,
state.
he's not going backwards. He wants to get to his friend's place, so he wants to get further and further away from home. He's not turning around and going back. So it's always getting more. He's always getting further away from home towards his friend's house. Does that make sense?
So it's like they can't do it. So it's
Yeah.
like to go back and back.
Yes. All right. Can we find a function for Michael's speed at any time?
Yeah.
How? Hugo?
The distance over time.
Derivative
No, derivative.
Derivative function. Which is your distance over time. So we want our derivative function. So you're just going to differentiate that function, and that tells you your rule to calculate how fast he's going at any particular time. All right. Michael's acceleration is the rate at which his speed is changing with respect to time. So we'll go into this in more detail, but initially he's going reasonably fast. Now he's going slower, faster. All right. So acceleration is just saying what's happening to his speed. His speed has his speed increased or decreased?
Increase, decrease.
That's a decrease of speed because he was going this fast. Now he's going less fast. So he's decelerated. He's going even slower, probably around here. So his speed's got less deceleration. What's happening to his speed now? It's increasing. So he's accelerated. His speed is getting faster. All right. How can we interpret that's the second derivative? That's the change in speed. All right. So we're talking about change in speed. Can we find his speed and acceleration at 15 minutes? Could we get his speed at 15 minutes?
Yeah.
How?
Differentiate.
Differentiate.
The point.
Wouldn't a double differentiation be acceleration? Differentiate also.
That's right. So if we do the first derivative of the function and put in 15, it tells us how fast he's going. And then if we do the second derivative at 15, it's telling us whether his speed at that time was going to be getting higher or less. Whether he's at a point where he's getting faster or slower.
You mean like positive and negative?
Yeah, it's going to be a positive or negative number. All right. At what point do you think the hill was the steepest?
When he was going slowest.
when he was round here where he was going the slowest, the hill was the steepest. Unless he's likes to go faster up hills. All right. How far had Michael travelled at this point? Let's say it's at 10. How far has he travelled? A kilometre. All right, so at this point, and he's travelled a kilometre. So, yes?
With the graph, we'll see its time. The area on the graph would be the total.
If we're doing, yes. We'll get there at t for 10, and his displacement at 10 was 1,000 metres. All right, 1 kilometre. You let me know when we get to about 20 minutes and I will save it and then start again because it doesn't like long videos. Okay, does that all make sense?
Yeah.
All right. Okay, so let's now go through all the basics. Right, for a particle moving in one dimension, we're only going to consider things that are going in one direction. We're not going to be doing like projectile motion where you take your sine and cos components of velocity and everything. All right? So those that know what I'm talking about can go, all right. The rest of you go, that's good, we're not making it complicated. So we're either going to look at a particle that's going to go backwards and forwards along here, or up and down. All right, we're going to take a 0 point and say a particle's going to go up and it might go down and then up again. So we're going to do a motion diagram, but that's effectively saying that the point starts here, it goes up, down, up again.
And there's no y-axis?
No y-axis, not on a motion diagram, we're just saying it's travelling in one dimension. Sorry, 2 dimensions, one straight line. All right, so imagine a point starting at -3 here, and it travels up to 1, it turns around and comes back, and then it goes up to 4 and stops. So you can't see me going backwards and forwards on that, so that's why we do our line like this, we turn around and then go up to 4. All right, but we're describing something that's going along the line. Michael riding from his place to his friend's place.
We can go back.
He can go backwards, but we're not going to talk about going different directions. We're just saying, imagine it's just one direction, backwards and forwards along that line. All right? S of t is our displacement function. So this is the displacement function, gives the displacement at a point P from the origin at any particular time. And obviously time is always positive, we're not going backwards in time. All right, so our domain is limited. Okay? The displacement tells us the distance or the displacement from a point. All right? And that's usually going to be from the origin. So we're going to say, now, here's our origin. Where are you with respect to that? So when the value of your displacement is greater than 0, what does that mean?
When the displacement is greater than 0?
Yes. It's moved which way?
Right.
To the right or above. All right, so this is our origin. All right, if our function says we're at +3, it means I'm 3 units to the right at that time. Okay, so that's the position. So it's the position is to the right or above the origin. Right? Whenever our displacement function is equal to 0, it tells us we're at the origin. We're at the 0, so we're at here. Right? We're at the origin here or there. And of course, if it's less than 0, where are we?
To the left.
To the left or below? Okay. So far, so good? So the question is, what is the difference between displacement and distance travelled? So this is where the physics people get the advantage because they know these sort of concepts. So Stu, how would you describe them?
Displacement is like where you are regardless of what you take.
Right?
You know, if you did zigzags, it wouldn't matter.
And the distance travelled?
It's just whatever route.
It's how far you've gone, yeah, whatever route. Okay, so here's the origin. Not just structures of my origin. Okay, so I'm going for a little walk. Walk, 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 walk. All right, what's my displacement?
Like a step.
I'm about 1 step from the origin. What was my distance travelled?
Long walk that.
A long walk. 1, 2, 3, about 10 steps. All right.
More than 2.
If I had finished over here, what's my displacement?
Still a step.
Minus 1 step. What is my distance travelled?
1 step.
1 step more than, like, assuming I'd done my big walking thing, it's 1 more step. So do I put a positive and negative with my distance travelled?
No.
You
No.
don't put it,
No.
you don't put it negative.
No, it's always positive, because it's always telling me how far I walked. All right? So this one is always positive, whereas our displacement can be positive or negative. What's the term that we're going to use to describe quantities where there is a positive or negative and those that are always positive? Okay? No, there's a term, this one starts with a V.
Okay.
This is a vector quantity. So a vector quantity has magnitude and direction. And this one starts with S.
Taylor.
Scalar, good job. So a scalar
Oh, scale.
quantity just has magnitude. So it just says how much. It's not implying or telling you anything about direction. So when I say I've travelled 11 steps, you've got no idea where I've gone, you just know I've travelled 11 steps. But if I said I was at +5, you know where I am, but you don't know how many steps I took to get there. It just says I'm this far in this direction from the origin. Okay? We do a whole topic on vector quantities later at the end of term 2. All right? Okay, happy with that?
Yeah.
All right, let me do this one example, then I'll save the video. Can I go to the next board?
Yeah.
All right, so here's our motion graph. Will this work?
Just so you know, this booth is coming up to 20 minutes.
Yeah, I'm going to do this board because it's a nice package, and then thanks for reminding me. Yes?
Quick question. What would be the derivative of acceleration versus time? So these
No, it's,
jerk.
what do you get?
Jerk.
Jerk.
Impulse.
The rate.
It's
Rate of change is zero.
change of acceleration, which is, yeah, we can't
It's not like
imagine
momentum,
it.
is it?
It's like a changing of your velocity. All right, so this is a link in your textbook. So I don't know whether on the video this will show, I don't think it will. So here's our point. We're starting whereabouts? What's our initial position?
Honestly,
We're at -3 units, 3 units to the left of the origin. It now moves. So it's going forwards all the time, all right? Has it got constant velocity? No, it looks like it was going fast, slower, slower. Oh no,
Other way
slower,
around.
fast, fast. Because the gap's getting bigger, it's going faster. All right? So, this is the equation for it. Our displacement function here is our S of t, t squared plus 2t minus 3. So I'll graph that over here. What are our domain restrictions?
It's greater than 0.
Domain is our input. Remember? T is greater than 0 or equal to 0. All right? So that means we only look at from no time when we're starting to any time. So this part graph starts here. That's all irrelevant. All right, so if you're on your calculator, you can just start at 0 on your window. You don't need negative time. All right, what does this tell us about the graph or about the movement? When we look at this, we're talking, this is our displacement, this is our time. Velocity is increasing. How can you tell that? Tangent's getting steeper. So here's our tangent getting steeper. All right, so it's getting faster. Can you see where it's starting? Where is it starting?
-3.
At -3. So think your y-axis is telling you where the point is. Imagine you are on the y-axis and looking where is the point. That's your y-axis becomes your motion graph.
So they start at 3 meters behind everyone.
So this point, whatever it is, a person or whoever, is starting at -3. All right. Where is it at time 1?
We're at about 1.5 seconds.
It's at 0, right?
At 0. If you factorize this, factorize your quadratic,
plus 3 minus 1.
plus 3 minus 1. So therefore, when is our displacement equal to 0 at time -3 and +1? We don't have negative time, so it's at the origin at 1 second or 1, whatever the units are. So here it is at this position at time equal to 1, time equal to 0. Where is it at time, I don't know, time 4, T4? Where is it? At time 4, it's about 20. All right, so our point has started here, gone there, and is going in that direction, and just getting further and further away, faster and faster.
I don't understand what this graph like split into 2.
Which graph? The top one?
What's the squiggly line?
I cut out that.
You can't be like negative time. Can't like before 5 minutes before I start
Oh, okay.
a race. You know what I mean? You can't like.
So what's the point of having it there?
Just to remind you that we don't, when you're doing these graphs, you don't do your negative time.
How
Well,
did they get that line then?
I graphed it from our function.
Oh,
So I was told this is a function describing how this particle is moving.
okay.
All right? I mean, there could be places where you do want the negative time. If you've got something already moving and you go, right, it's moving, I'm starting now. What was it moving before? I said now.
So why is it below, on the y-axis, why is it below 0?
Because that is our displacement. And this is saying at time 0, it is at -3.
So this was a race, like they would perhaps started from the line, but then this racer is starting just.
Yeah, he started before it.
Like 3 meters
He's got
before.
like a
and then-
handicap. Yeah,
Okay.
all right. So at time 0, S of 0 is -3. At time equal 1, we worked out that what's S of 1? 0. What is at time 2? What's S of 2? What's our equation? T squared plus 2t minus 3. T squared plus 2t minus 3. So S of 2 is, what was it? 5. Thanks. T3 at time 3, what is the displacement? All right, so that tells you where it is.
Would we have to draw those? The lines?
So you might be, sometimes it's good drawing a motion diagram to help you imagine what's happening. It's a bit like a sign diagram. You're not always going to be asked to draw a sign diagram or draw a motion diagram, but sometimes I use it to help me see what's happening. So this is a motion diagram or motion graph. So we worked out at time 3, it's at 12. That was at t equal to 3, and it's at 5 at t equal to 2. All right? And I'm going to